Welcome to Code Report. I'm your host, Connor Hoekstra. Let's take a look at the contest that happened last week.
Reviewing last week, we had quite a few contests, 4 from Codeforces, 1 from HackerRank, and the weekly contest from LeetCode. Note that I didn't miss round 464 in last week's episode. Codeforces announced that contest within the 7 days in between my last episode and this one. So if you follow me on Twitter, I'll be giving updates when contests like that are announced. Taking a look at the top 10 leaderboards, we're going to do this in 2 parts, seeing as there were so many contests. The first part will cover the Codeforces leaderboards. I've highlighted in colors those users who have shown up on the top 10 in multiple contests. We can see Umnik had 2 places, first and third. He's ranked second on the overall in the contest. We have the 10th ranked Fate Ice, who finished 4th in the Div 1 462 and second in round 463. And we have the 11th ranked Dotaria. I'm hoping that's how you pronounce it. Ranked 5th, 2nd, and 1st in 3 different contests. KRK ranked 3rd and 8th, and then UE placing 7th and 9th in Educational 38 and round 464. Second part of our top 10 leaderboards, we have the contest Rookie Rank 4 from HackerRank and LeetCode contest 72. UE placing 3rd in the LeetCode contest. And in today's video, I'm going to be covering 2 problems from the HackerRank Rookie Rank 4 contest, problem 2 and problem 4. And I'll be covering 2 problems later on this week, the final problem from the Rookie Rank contest and the last problem from LeetCode contest 72. So let's take a look at our first problem. Our first problem is problem 2 from the HackerRank contest Rookie Rank 4 entitled Server Safety Room. The problem states you are given an array of server positions and server heights. If any rack reaches another rack when it falls, it will cause the other rack to fall as well. Safety rules require that at least some of the racks should remain standing if one of the ends falls toward the others. Your task is to determine whether either or both ends will cause all racks to fall should one be tipped. To determine if a rack will knock over another rack, use the following rules. Complete the function checkAll, which takes the positions and heights of the server racks as input and return left, right, both, or none, representing which of these ends is unsafe. So let's take a look at our example. In this example, we're given 2 racks, one at position 1 and one at position 3 with the heights 4 and 1 respectively. And we can think of this problem as basically as a game of dominoes. So our racks are dominoes, and we are going to push from the left and push from the right. And if either one of those is going to result in all of the racks toppling over, we need to return left, right, or both based on that. So you can see here at the bottom, the answer to this problem is left, and that's because if we topple over the rack towards the right at position 1, it will also topple over the rack at position 3. But if we were to do the reverse of that, toppling from the right towards the left, our rack at position 3 isn't going to topple over the rack at position 1. So that's the gist of our problem. So let's take a look at a less trivial example that might have tripped some people up. In this example, we have 3 racks at position 1, 4, and 6 with the heights 2, 2, and 10. And so you can see at the bottom, the answer to this input should be right. However, if you implemented your algorithm only checking adjacent racks, it would return none. And that's because toppling from the right towards the left, the rack at position 6 would topple over the rack at position 4, but the rack at position 4 will not topple over the rack at position 1. However, the rack at position 6 will also topple over the rack at position 1. So we can't just check the adjacent racks, we also need to sort of keep track of the maximum position at which a rack will topple over. And we'll see that when we look at our code. So let's do that. So you can see here we have our checkAll function. We have 3 inputs, n, which is the length of our height and position vectors, and those are represented by the h and the p. And so at the top, we are initializing our string result, or res for short, which we are going to return at the end. It's initialized to none, and if we don't basically figure out, or if we don't have any racks that are going to end up being completely toppled over from either one of our left or right directions, it'll stay as none, and that will be returned at the end. So we declare a Boolean allFall initially set to true, and this m, which will represent either our maximum or our minimum. For our first loop, it'll represent the maximum. For our second loop, it'll represent the minimum. And so you can see here, basically all we're doing is we're checking, we're initially setting our max equal to its current value or height plus position, which is going to give us basically the maximum position to which it'll topple over another rack. And then if at any point our next position is greater than that value, we know that we basically have a gap and all of them are not going to topple over. So we set our allFall equal to false. And then after this loop, if allFall is true, we set res equal to left. And note, we could break out of this loop at this point, but that adds an extra 2 lines of code, and our solution is still going to be linear regardless, so we don't need to do that. And then we come down here to the bottom half of the function, we reset our Boolean to true, and then now m is representing a minimum, not a maximum, so we're going to set it to be just above the maximum value, and we basically do the same thing, set our value m, and then check in this case if m is ever greater than the next position, which in this case we're looking to the left, whereas here we were looking to the right, based on our direction of which we're toppling. And same thing, if it satisfies this condition, we set our Boolean to false, and then we set our res based on that. So if we've already set our res to left and all of them are falling from toppling in the leftward direction, we're now going to set it to both. Otherwise, just set it to right and return that. And as previously mentioned, this solution is linear because we have only 2 loops. The next problem we'll be covering is problem 4 from HackerRank 4, entitled Winning Hand of Cards. The problem states you're at a party and the host has arranged a game of cards. You are given a number of cards and try to create as many combinations from those cards as possible that result in a winning hand. A winning hand is one where the product of the number on the cards modulo a given value, the modulo divisor, is equal to another given value, the target value. Complete the function winning hands to return an integer denoting the number of winning hands. And note that n, the number of our cards, is between 1 and 30. M, our modulo divisor, is between 1 and 10 to the power of 6. X, our target value, is between 0 and 1 less than our modulo divisor. And the number on our cards is between 1 and 10 to the power of 7. So the example given by HackerRank is the following. We have 3 cards, our modulo divisor is 3, and our target value is 2, and each of the values on the cards is 2. So it shows you here all the possible sets that we can get from those 3 cards, the 1, 2, and 3 representing card 1, card 2, and card 3. And below shows the target, or the value from the operation performed on all of our sets. So that's multiplying the value on the cards in our set and modulusing that value and seeing what we get. So for 4 of them, we get our target value, the first 3 and our last one. So this would return 4. So the naive approach to this problem is just basically to generate all the permutations or basically all the sets of cards and perform this operation and check if it's equal to our target value. So I'm going to show the code for this very quickly. I'm not going to spend much time on it because I want to get to the correct solution, but I think it's illustrative of a couple tricks that could be useful in future problems. So this is the code. It's pretty short. We just initialize n, which is the size of our vector, and answer, which is what we're going to return at the end. And basically what we're doing is we are creating 30 different bit masks, and this will have, for the first iteration, 1 1 and 29 zeros. So this is going to generate every single set that only has 1 card in it. The second bit mask will have 2 1s and 28 zeros, and these are going to generate every single set that only has 2 cards in it, so on and so forth. And so this will go until we have 30 1s and no zeros. And so the way the bit mask works is we're going to declare our result which might be equal to our target value at the end. We initialize this to 1. And if in our bit mask our value is equal to 1, we are going to basically apply that value multiplicatively to our result, and that value is from our cards. So the bit masks works with our vector, so they have the same length, and basically the 1 or 0 represents whether or not that card is going to be included in our set. And we basically just combine this with our algorithm function pre-permutation. There's also a next permutation, and what this is going to do is it's going to permute our bit mask until we have gone through every single one. So for the bit mask where it starts with a 1 and then is followed by 29 zeros, it's just going to move that 1 to the second spot and then to the third spot and the fourth spot until it can't be permuted anymore. And we're using previous permutation because technically we're starting with our bit mask sorted in reversed order. If we started with the zeros and ended with the 1s, we would use next permutation. So this won't get you a full solve on the problem. It will get you partial points, and that's because the complexity of this algorithm, the 2 for loops here is going to give you all of our basically sets of cards, which is going to be 2 to the n, and the inner loop is linear. So our total complexity is n times 2 to the n, and this definitely is going to fail, but I think it's, like I said, illustrative to show it. But let's look at the correct solution. So this solution uses dynamic programming, and we're going to slowly walk through this problem to hopefully illustrate what it's doing. It's very similar to the editorial solution, but I think it's a bit easier to understand. So off the bat, we are going to construct this 2D vector. The first dimension is 2 and the second dimension is m. And the 2 is because we're representing 2 different states. We don't really need to do this. We could basically have 2 local vectors and copy one from another, but it's just easier to store them like this. So this grid basically is representing this. We have 2 states and we have all of the modulus values. So basically, after performing the operation on our set of cards, we know that because it's going to be modulus 3, the only possible values for our answer is going to be 0, 1, and 2. And we'll use this to basically keep track of which sets of cards give these values, and use this and basically the current number of sets to in a much faster way get to our solution. So we've constructed our vector, and now we're going to come into our for loop. And so in this example, I'm going to use a little bit of a less trivial example. So our card values are not 2, 2, 2, they're 2, 3, and 4. Our modulus divisor and our target value are still the same. So for our first loop, it's going to be pretty trivial. So you can see that basically our 2 operations are copying one state to another. So because we don't have anything, nothing's going to happen here. And we're doing also a plus equals from one state to another state, but because once again in our first iteration we don't have anything here, this is going to do nothing. So basically we're going to skip down to this line, which is saying for our current state, take ai modulus m and do a plus plus there. So what that's going to do is add the value 1, because for our card value 2, if we were to make a set of just that 2 and perform our operation, it would give you a 2. That's basically what this is. It's 2 modulus 3, which equals 2. So then we're saying if we only had a 2 in our card, so we only had the card 2 when we didn't have 3 or 4, we'd only be able to generate one set, and that's the set of a single card 2. And so we would end up with a 1 here, and then we would end up returning 1 as our answer. So for the moment, we're just going to pretend that this 1 represents a set of 2. And let's move on to the next iteration. So we switch our state to state 1, and then we're going to come into our next iteration. So now AI is equal to 3, and we've copied our state 0 over to state 1. Note that this caret here is just the bitwise OR, and all that does is changes the state from 0 to 1 if it's 0, or 1 to 0 if it's 1. So another way to do this would be 1 minus state, but I think bitwise operators are a little bit faster than arithmetic operators. And so now we're going to step down, and this is the first time that our second sort of operation is going to do much. It's not going to be completely clear what we're doing here, but on the final iteration of the loop, it should be a lot more clear. So you can think of J as basically checking our set of, or our set of sets, as if you can think of the current sets that give you this result. So for 0 and 1, we don't have any sets down here that are going to give us this result. The only set that we have is 2. So we can basically skip our first 2 J's. And when we come to 2, at this point, now we do have something here. So we're going to go J is equal to 2 times 3, which is 6, modulus 3 is going to be 0. And so we're going to take the value that's here and put it here. And basically what this is doing is it's saying if we were to add our 3 to all of the sets for each one of these sort of modulus groups. So there's nothing here for modulus group 0 and 1, but for 2 there is. We have the set that's just 2. So if we added a 3 to this set, what would we get? And the result is that adding a 3 would change the modulus group from 2 to 0, because 3 is divisible by our modulus divisor. And so we're basically taking the number of sets that we have, which is just this 2, adding a 3 to it, and then storing the result here. So you can now think of this 1 as representing the set 2, 3. And that's basically how this algorithm works. So at this point in time, well, I guess we have to move to the next step. So this is adding just the set of the 3. So 3 modulus 3 is 0. So we add this set here. So now we have 2 sets in our modulus group 0, and we have 1 set still in our modulus group 2. And so if our vector only had the cards 2 and 3 in it, we'd use this table to return our result. So it would still be 1 because our target value is 2. If our target value is 0, our answer would be 2. So let's move to the final iteration, and hopefully this will really make this algorithm crystal clear. So we've switched our state back to 0. We're going to copy our state 1 into state 0, and now we're going to come back down to our second operation here. So for j equal to 0, 0 times 4 is 0, modulus 3 is equal to 0, so we are going to add basically the 4 to all of these sets, and it's still going to give us a modulus group of 0. So basically we're going to double the number of sets we have in our modulus group by adding 4 to it. So this goes from 2 to 4, and our sets that are in this modulus group doubles. This is why we're always doing a plus equal of basically the modulus group that we're looking up. And so now we're going to move to j equals 1. Once again, we don't have any sets here, so we're not going to do anything for this modulus group. And for 2, 2 times 4 is 8. Modulus 3 is going to be 2, so we're going to be doubling the size of this modulus group as well. So this goes from 1 to 2, and we add the 4 to all of our sets here. And finally, we're going to skip down here. We're going to do 4 modulus 3, which is going to give us 1, and so we're going to do a plus plus to here, and that's going to give us 1 and our set 4. And so now we basically have finished our algorithm. So that's sort of how it works. Each iteration depends on the previous iteration, and it keeps track of the number of sets in the modulus group. That's what the J represents. And at the very end, we basically have to perform a bitwise operation on our state because we changed it and we want it to be in the state that we finished. So at this point, it's switched to state 1, but we really want to look at state 0 because that's the last time we performed this iteration. And then we are going to look up our target value, which is 2, and that is the number of sets that give us that modulus or target value is 2. And the complexity of this solution is going to be quadratic, but not really n squared. It's going to be n, which is the length of our vector, times m, which is our modulus, so the number of modulus groups that we have. So the last thing to do is to take a look at the contest upcoming in our next week. So tomorrow we have a Code Forces round 465 at 11:35. On Tuesday we have a Top Coder single round match 7:30 starting at 7 a.m. On Friday, we have a university code sprint starting at 11. That's put on by HackerRank. And not the last contest of the week, but it usually is. We have our Leak Code Contest 73 at 9:30. And finishing off the week is a contest early Sunday morning at 9:35. And as always, taking a look at our top 10 viewing countries, the top 6 didn't change this week. Netherlands a newcomer at position 7, Brazil dropping 1, Lithuania dropping 2, and Sweden jumping up 1 to 9th place. So thanks once again to everybody for watching all around the world.
As always, if you enjoyed this video, hit that like button. Make sure to follow me on Twitter for reminders 30 minutes before contests start. You can find all of the code that I use in my videos on my GitHub page. All of the links are in the description down below. And finally, if you want to make sure you don't miss any of my upcoming videos, make sure to hit that subscribe button. Thanks for watching, and I'll see you in the next video.